All right, hello people watching at home, which should be all the people who are not here, which should be all the juniors plus other people. What you missed because I was too lazy to make a recording, but then I got guilted into it, is a long rambling discussion about the history of the mystical properties of the Platonic solids, Kepler's mumbo jumbo, also other various things. Also a quick recap of Euler's formula. What we will now do, without further ado, is prove that there are only 5 Platonic solids. Are you ready, class? Yes. Good, let's do it. Okay, first, some quick notation. So let the number of edges in the planar embedding be E, or epsilon. Let the number of vertices be V. Okay, so that's kind of like a little bit annoying because usually we use N for that. Let's let the number of regions be, so aka faces, be R. And now, what makes a Platonic solid, may I have one of these, is that not only must the faces be regular, but they have to be the same kind of regular, and all congruent to each other. And also, every vertex needs to be regular in the sense that there are the same number of polygons meeting at that vertex. Cool? Okay, so let's let n be the degree of each vertex. So the degree of each vertex, let's call that n. In other words, what is n for an icosahedron? Jason, what's n for an icosahedron? 5, yep, because every vertex in the icosahedron is 5 edges. Okay, and then the last thing is, let's use the letter B to refer to the number of edges bounding each face. Number of edges bounding each face. Let's call that B. In other words, just the number of sides in each of the polygons on the thing, on each face. Okay, well, this is pretty cool. Here's what we are going to do. First, we are going to apply Euler's formula. So if we apply Euler's formula with this new kind of notation, it says that the number of faces / regions is R. So R is the number of edges, which is epsilon, minus the number of vertices, V, plus 2. And now the goal is to rewrite V and R in terms of epsilon, n, and V. So this is what we're going to do. Express V and R in terms of epsilon, n, and V. Okay, well, how are we going to do this? What can I say about V, for example? V represents the number of vertices. What does the number of vertices have to do with the number of edges, the number of edges bounding each face, and the degree of each vertex? Yeah, all right. It's pretty much handshake, right? Yeah, by handshake. He says, handshake says that the total, that if you add up all the edges in a graph, you're going to count every vertex twice, right? The degree of every vertex twice. Yeah, so by handshake, if you take the total number of vertices, which is V, and what is the degree of each vertex? N. So if you multiply the number of vertices times the degree of each vertex, then this represents the sum of the degrees of all the vertices. Yeah? So the sum of the degrees of all the vertices must be twice the number of edges. Jason, you good? Okay, so that means we can solve for V. What's V? It's 2 epsilon over n. Okay, and then by just there's no real theorem for it. We can also look at each face one at a time, and we can talk about the number of edges. So on the one hand, if I take the number of faces, so there are faces, right? And there are B edges on each face. So if I multiply the number of faces times the number of edges on the boundary of that face, what do I get? So R represents the number of faces. So like a dodecahedron is made up of 12 pentagons, right? So if I take the number of faces, which in the dodecahedron case would be 12, times B is the number of vertices on the edge of each, or number of edges. Yeah, the number of edges bounding it, so that's 5, right?
Yeah.
So if I multiply the number of faces times 5, what do I end up with?
2e.
Yeah, 2 times the number of edges. Because I've counted every edge twice, right? Because every edge on the dodecahedron is a member of 2 faces. Yeah, does this make sense? It's like not so hard, right? Okay, good. So what was I trying to do again? Oh yeah, express R. So R is 2 epsilon over B. Okay, and basically I'm going to take this, and I'm going to take this, and I'm going to stick them into Euler's formula, and I end up with, let's see, 2 epsilon over B is R equals epsilon minus 2 epsilon over N plus 2. Is that what I wanted to do? Sure. Yeah. Okay, and now it's like I want to kind of simplify things a little bit. So I'm going to divide through, okay, this is not obvious, but Gossett says, yo, just do it. Divide through by 2 epsilon. I think you guys can handle this advanced algebra 1 type problem. Can someone make sure it's still framed? Okay. So we get 1 over B equals, what is that, 1/2 minus 1 over N plus 1 over epsilon. Did I do that right? Yeah. Okay, and let's just make everything positive because that's fun. So I have 1 over B plus 1 over N equals 1/2 plus 1 over epsilon. Okay, so this seems like some deep relationship between B, N, and epsilon. So the number of edges bounding each face, the degree of each vertex, and the total number of edges. Okay, so now this is kind of cool because if you think about this, these two fractions have to add up to more than 1/2. So intuitively speaking, if B and N are big, then that's bad, right? If B and N are large, and I'll just leave that big, then no. Okay? If B is like 7 and N is like 10, then that just can't be, right? Because then those don't add up to more than 1/2. So already, who's with me?
Yeah.
Already I feel that the only solutions to this equation, so every Platonic solid must be a solution to this equation. So this is like a Diophantine equation, right? We're looking for all these things have to be integers, right? B, N, and epsilon all to be integers. So we're looking for all solutions in integers to this equation. And we realize that B and N must be kind of small, on the small side, because otherwise it won't work. All right, so now we basically just crank it out. So let's make a little, let's see, can I fit it in here? I think I can. Let's make, can you move the camera and I'm going to make it bigger over here?
Yeah.
Okay, or maybe it just fits already. Okay, so let this be B, let this be N, and we're going to just kind of do this. So we'll call this 3, 4, 5, and I'll add more if I need to, hint I don't. Okay. Alright, let's talk it out. Do we know any Platonic solids in which N is 3 and B is 3? If B is 3, it means that the number of edges bounding each face is 3. In other words, triangles. N is 3 means that 3 triangles meet at a vertex. It is the tetrahedron. Tetra. Okay, and also, while we're here, let's just check all the things. So if that's N and that's B, what should E be? So 1/3 plus 1/3 is 2/3. So if that's 1/2, then this has to be 1/6, right? And so E has to be 6. Are there indeed 6 edges in a tetrahedron? Yeah. How about V, the number of vertices? Well, what is V? It's 2. Oh, what's N? Maybe we should do that first. Wait, what the hell? Oh, N is 3. So V is 2.
It's just 4.
V is just, but I'm using the formula, right? Instead of like using my knowledge. So V is 2 times 6, which is 12, divided by 3, which is 4. So V is 4. Are there indeed 4 vertices in a tetrahedron? Yeah. Is there anything else to say? R, I guess. What's R? R is 12 over 3, which is also 4. And indeed, there are 4 faces in the tetrahedron, so it's all working out. Okay, let's do another one. How about this one? N is 3, B is 4. Heard of that one before?
The two.
Wait, N is 3, B is 4. If B is 4, yeah, B is 4 means the number of edges bounding each face is 4. In other words, squares. So squares and 3 squares meeting at each vertex. This is the cube. Okay, let's figure out all the crap real quick. Let's see, so this is 1/3 plus 1/4, right? Or did I do it the other way around? Yeah, 1/4 plus 1/3. Either way, it works out to be 7/12. So if that's 7/12, then that would be 1/12, right? Is everyone following this advanced fraction arithmetic? Okay. So epsilon is 12. Okay, what's V then? Using the formula, it would be 24 divided by 3. So it would be 8. Are there indeed 8 vertices in the cube? There so are. And R would be 2 times 12 over 4, 6. And there are indeed 6 faces in the square. Okay, a couple more to go. What about, where do you want to skip around, or do you want to move over here?
No, 3 and 4 work, then 4 and 3 have to work.
Yes. Okay, sure. She says that, but yeah. Yep, she says that like if 3 and 4 work, then 4 and 3 have to work. Okay, good. So let's go over here. What if N is 4 and B is 3? What's that? Yeah, now that's the octahedron, right? B is 3 means triangles, N is 4 means 4 triangles meeting at each vertex. So this is the octahedron. This is so much better than Gossip's presentation. Okay, what's epsilon? It must indeed again be 12, right? Because it's the same math. Well, if that's the case, then the number of vertices, I'm just using the formula, 24 over 4 is 6. Are there 6 vertices in an octahedron? Yes. And then R would be 24 over 3, 8. Are there 8 faces in an octahedron? Yes, that's why it's called octahedron. Oh, we are having so much fun. Let's do this one. What is this one? If B is 3 and N is 5, so triangles, 5 meeting at each vertex, what's that? Icosahedron. Icosahedron. Exclamation point. What is epsilon now? Epsilon. Oh, this one's fun. So 1/3 plus 1/5. Damn, we just made it. That's only a tiny bit more than a half. That's 8/15. Good job, Ari. 8/15. So if that's 8/15, then 8/15 is how much more than a half?
1/30.
1/30th more. Damn. So epsilon is 30, and indeed there are 30 edges in an icosahedron, in case you didn't know that. How many vertices? It's twice that number, so 60 divided by 5, so that's 12. That doesn't seem right.
Nope, it's 20.
Let's try that again. I think I did something wrong. 60 divided by 5.
No, it's 60 divided by 3.
60 divided by... What am I doing wrong?
Oh,
There are
12 vertices.
Did we screw something up? Are there 12 vertices only?
Yeah,
How
I
many?
think
No
we
way.
did the wrong solid, sorry.
Did we do the wrong solid?
No, it's,
No,
we're
we're
fine, it's
thinking of
15
the-
and
C
then
is-
20.
3 is...
D is 15 and R is
Why is B 15? 60 divided by...
5.
It's
60
12.
divided by 5 is
I
12.
meant to say 12.
Wait, are there 12 vertices
There are
in
12.
icosahedron?
There are 20
Yeah, there-
faces.
There are 20 faces and 12.
Are there only
There's
12?
12, yeah.
Yeah, it's like
Math was right, my brain was just broken, yeah. There just are only 12 vertices. For some reason I felt like there were way more.
There's more in the...
Yeah, you're totally right. Whoa. Okay, good. I'm also hungry. I'm getting stupid. Okay, R is, what's R? R is 2 times 60 divided by 3. That is 20, and indeed there are 20 faces in my Constitution. Good job. Okay. Yeah. Yeah, there are. Count them. It's in your hands. It's like 5 and 5 and 5 and 5. Okay, good. Last one, maybe. Don't want to ruin the suspense. The fifth, so I'll just say the fifth one. The fifth one is when B is 5 and N is 3. So that means pentagons, 3 meeting at each vertex. That is the dodecahedron. Wah, wah. Oh, it is epsilon. It is going to be, oh, it's still 30, right? Because, like, again, it's like symmetrical. Yeah, yeah? Say yeah. Okay, what is V? V would be twice that number, 60 divided by N, which is 3. So it's just 20 again, right? Yeah, so that's kind of interesting. Oh, I just learned something. And R is then 12. I don't even need to do it because it's just a repeat. They're like related to each other. In fact, that's coming. Okay, so now that has been established. Well, are there any more? Lyndon, more? No, why not? It's just a thing for me to explain. This was the whole point of going through all this crap was
that way, like those numbers are bigger. It's like not gonna add to be more than half.
yeah, it's just so you just need to analyze this equation. If this is 4 and this is 4, for example, what's 1/4 plus 1/4? It's already a half, so then we have no solutions for epsilon. So I can't have the 4/4. What about 4/5? No way. 1/4 plus 1/5 is less than half. Do you guys appreciate? No, do you appreciate the beauty of this argument?
Are you going to use math?
What if you have?
I'm using math right now. I'm just not writing it down. But I'm just saying that if B and N are each greater than or equal to 4, then the left-hand side of the equation is already greater than or equal to a half. Is already less than or equal to a half. And if the left-hand side is less than or equal to a half, it has no solutions. Was that better math for you?
Yeah.
So the rest of this chart is just no. So by the fact that there are no other solutions to this equation, I have demonstrated that there are only 5.
Well,
Are you impressed?
We didn't prove that if N or B is 3, then, I mean, I guess that's just like more tedium. If one of them is
Oh, that's
3,
true.
then one of them
That's true. We should go on.
Wait,
How about this one?
no, that's still not gonna work.
That adds up to a half.
That also adds up to a half.
Yeah.
But yeah, he's right. For completion purposes, we should argue that.
It is so bad.
It is so bad.
I think that's really, really cool. Okay. It is pretty, it's all like symmetrical, it's like interesting. Okay, good. That was something we were going to do last class. This class, I want to talk about this thing called the chromatic number. I think I want to do that first. Yeah.
Is this like the coloring?
Chromatic numbers. Coloring is
Yeah. Alright. Can someone turn the camera around?
No, I got it. I got it. Wait, should it be?
Yeah.
It doesn't have to be like parallel to
It
the.
doesn't have to be perfect. It just has to be the whole.
Your head
It's fine, but it's kind of terrible. It's better if you like move it a little bit.
No, Candy hasn't changed.
What? No.
You can actually see the
Okay. So
view screen down.
okay. So
On this one?
you might have heard of this thing called the 4-color theorem. Raymond, you heard of it? Why'd you say, oh no?
Oh no, they have like some weird
Oh, you read the book already.
Yeah, well, that's what you said to do.
Oh, I did. This is a famous. Did I tell you to read this section?
Yeah.
Oh, oops. Okay. This is a famous.
See something that's good to be.
This is a famous proof in the history of the philosophy of math. Because, oh yeah, what is the 4-color theorem, you might ask? Well, anyway, suppose you are going to make a map, let's say of America. I cannot draw America, so I'm just going to do this. I think I left out Texas.
We don't really need Texas.
I don't
Where's
think
that?
that's
What about Hawaii and Alaska?
Okay, so we don't need that because they're not connected. Okay, so here is America. And America has like a bunch of states in it. And they look, you know, kind of like this or whatever, right? Good.
Nevada.
Good. Okay, so now I would like to, it's funny, you can try to make like really good jokes and then nothing's as funny as just being really stupid. Okay, something about comedy. Okay, Noah Feng, you like this. Well, guess what, Noah Feng? What we'd now like to do is we'd like to color this map. Okay, and should we just like try this?
Why?
Sure.
You are blue, you are green, you are red, and you are purple. Go. You have 1 minute to color this map. And the claim is, and this is what the four-color theorem says, you have to work together a little bit. The claim is that any map can be colored with merely 4 colors. And of course, the proviso is that we do not color adjacent states the same color, because that would be a crappy map. Agreed?
Sure.
So this guy, according to the legend, this guy just sat there trying to make a map, realized that he only needed 4 colors, tried to come up with a map that required 5 colors, couldn't do it, and proposed this conjecture called the 4-color theorem, which is that any map can be colored with just 4 colors. This defied proof for a really long time.
It's like green.
Looks like they screwed up. So it's kind of fun.
Canada.
Oh my gosh. Home state. Is that really nicely?
I think, no, one's red, one's blue. So you draw green.
How'd it go?
State.
We're getting Mexico, right?
Oh yeah.
Wait, did it work?
Yeah, you gotta draw the eagle, and then here's the.
Okay, good, sit down.
Aw.
What is that? What's going on? Oh, I see. Metro Canada. Okay. A round of applause.
Who drew these? Started
Good.
Guys, there's 2 red states.
If elected, this will be our new America.
Wait, that's wrong. Wait.
Oh, did they screw up?
No, that's easy. That's easy.
No, what happened?
Actually, it's not.
Like, Sama was the one.
Oh, wait.
I found it in a new state.
Okay, so actually they screwed up. So it did not claim that it was easy to do this algorithm, but or that even that there is an algorithm. But it seems it is actually true that 4 colors suffices. Okay, so how can we? What's this weird noise coming out of? Oh, it's coming out of my own pocket. Okay. Whoa. Okay, so what we will do in order to start being able to talk about this, instead of talking about states being, because states in fact are like regions, being colorable, instead what we will do is we will talk about each state as being like a point. So I put a dot in the middle of each state, and basically what I want is for adjacent states to be different colors. Well, if I want adjacent states to be different colors, then what matters between any 2 states is whether they share a border. And if they share a border, well then they should be different colors, yeah?
Sure.
So if I think of every region as like a point, then those 2 regions are adjacent in the sense of sharing a border. Or if they are adjacent in the sense of sharing a border, then I want to put an edge between them.
Wait. So are are regions not like adjacent if you like say you have like a cross, right?
Okay, yeah, and that's another thing that comes up. You're not allowed to have a cross, right?
Okay.
Because if you have, because obviously, yeah, because you couldn't have some weird country in which you had like, you know how we have that little, there's like a famous thing called like the point in America where you can step on 4 states.
Yeah,
It's like the
4 corners.
4 corners. Yeah. Just like 4 corners across the street, but that one. So you could have some weird country with like 5 corners, then you would think that maybe 5 colors were required, right? So you say that's like not allowed or whatever.
Wait, so what's not allowed? So
You can't-
anything more than a cross?
You can't have points.
Yeah, there's that. Like that.
Well, depending on how you look at it, you either have to argue that this can be red and this can also be red, even though they're sort of meeting at a point, or you just have to exclude that from the conversation.
So what are the requirements? Are there no crosses at all?
Of this class.
What's a cross?
What do you mean by cross?
Like-
There are a couple of things that
There be like-
need to be allowed. For example, you can easily, if you want to be very devious, you can imagine a map that does require 5 colors. How do we do this? You could have a state. I gotta think about this for a second. And
You have to put like states inside of states.
you have to put states inside of states, but I can't think of it on the spot. If you have a state, and then you have another state inside of it.
Oh, okay, I think I got it, maybe. No, I think. I'm trying.
And if you have another state inside of it, but then maybe you have another state
Well, if you just have a-
inside of that.
If you just have the big
We just
state.
keep going.
You know, if you just have
I
the
think
big
if I
state.
keep doing this, I'll eventually need more than 5 colors, right?
If you just have a big state with 4 states inside of it.
No, but
No,
then they
because
could be all different.
You can't have the corner.
No, but like,
Because
How
to
can
get
you-
No, but then what are you gonna color the big
like
state?
4 adjacent.
Oh, okay, so what
yeah.
you're saying is big state, and then,
And then yeah.
No, yeah, just like that.
Yeah.
No, because
that.
you can only use 3 because the 2 on
Yeah.
opposite corners. Because
so,
of the
so
corner
like, once they're
rules.
diagonal to each other,
Two
those
opposite
aren't
corners
technically
aren't
adjacent,
touching.
right?
No, just draw some.
I'm pretty
Wait,
sure.
how about that?
No, because
No,
then the
this-
bottom
here,
left and top
Mr.
right
Rose.
can be the same.
Oh,
color.
okay, so I need to do like this.
Yeah.
No, but now the outside isn't touching the top
No,
left.
just
The inner outside.
Yeah, yeah,
This is a
Which one?
theorem.
Oh, this one?
No,
No, the top left one.
okay, not the one you wrapped around, the one
Like-
under the one you wrapped
like
around.
It needs to be touching which
This
one?
this doesn't touch the outside one anymore. So
Oh,
this look
okay,
at a
okay,
different
okay.
color.
Okay, so I need it to go.
But then you can't punch out, it's like you're gonna enclose one of them.
Conditions.
Yeah.
So wait, what are you trying to tell me?
Mr. Rose,
Is this an what?
aren't you trying to disprove
Yeah,
that
you're trying to just.
I know, what I'm trying to explain is, I'm not trying to dispute the theorem, I'm trying to explain why one of the requirements is necessary in order to state the 4
The
color
4
theorem.
corners.
What
No.
is the?
Wait,
the requirement
I thought it was
is
just in a plane.
connected?
Because if you consider all 4 of these to be touching,
Then-
they're-
then-
Someone look up the 5 color theorem and look at the technical details. There's a footnote that's like, we have to exclude, and I think one of the reasons is states within states, and I was trying to figure out what the reason was for that.
Because look, if you allow corners.
No, but are we not allowed?
Yeah,
are we
but
not
think
allowed
if you
crosses?
allow corners.
Yeah, if you allow.
If you
crosses.
consider
Anyway,
corners
someone's
to be
gonna look it up.
adjacent,
Meanwhile,
separate them.
so okay, there are some technicalities which we're gonna go back to in a second because you guys love your technicalities. But anyway, wait, hold on. What are the technicalities?
Corners aren't adjacent.
Corners aren't adjacent, so that's just a stipulation that corners aren't adjacent, and that's it.
I don't see anything else.
I thought there was a rule that said you can't have a state within a state, but I don't remember why. So maybe I'm just misremembering. Maybe that's not a rule.
no.
Anyway, shall we return? Shall we return?
5 colors.
If you have a counterexample, then what?
I don't think you can require 5 colors of that because eventually you're gonna get the case where one of them is fully inside of another. At which point the innermost and the outermost can be the same color.
No, I think you can do it.
Okay, can you draw it? And when you're done, that's great. Okay, good. The point is, wait, hold on. I want to make sure we keep on moving forward here. The point is that what we will now do is we will draw a edge between 2 vertices if and only if those 2 regions share a border. Does this seem like the intuitive thing to do? Because if 2 regions share a border, then those 2 states are adjacent. Is this making sense what I'm doing? Please say yes.
Yes.
Okay, good. So, and really, instead of saying that that adjacent states must be of different colors, it is more simple from a graph theory perspective to rephrase the problem in terms of each. I missed a couple. Okay, I missed a couple. Who cares? It's good enough. So the point is that each region will be associated with a vertex, and an edge will be drawn between 2 vertices if those 2 regions share a border. Then what we have is the question of how many colors are required to color a map reduces to the problem of how many colors are required to color vertices such that no 2 adjacent vertices have the same color. Who is with me? It's not so hard. Okay.
Countries have to be a contiguous area. So like Michigan or something, you know how it's like two different.
Ah, okay. So you can't have like Michigan or like the Russia situation, right? With the Kaliningrad or whatever. Okay, so no islands and stuff like that. So because if you were allowed people to have all kinds of pieces, then it could be
Yeah.
crazy. That's the only requirement. And the corners thing.
Yeah, and it's planar. It's on a
And
plane.
it's planar, right? So it's not.
Yeah.
Yeah, you can't have a country underneath another country. But which actually is like a thing, by the way.
What?
I can't break it.
Yeah, like certain countries like
I
don't
think
control their
I couldn't break it
airspace, you
without
know.
breaking continuity. So I think
Apparently, you guys haven't spent a lot of time reading the details of like the various like Israeli Palestinian proposals. Like for example, that like one of the states would have the Temple Mount, and the other one would have like underneath, and the other one would have the air. It's like the whole thing. All right. Good. We're learning so much in this class.
the only way to get that, so that's
So,
tuning.
back over here to the math. What is the chromatic number? Can I just say it without writing it down? It is the minimum number of colors in a simple planar graph required to color all the vertices such that no two adjacent vertices have the same color. Would you like me to say that again or write it down? I could, but I don't want to. The chromatic number of a graph is the minimum number of colors. So it is the minimum number of colors required to color every vertex. So that color every vertex such that no two adjacent vertices have the same color. Okay. The minimum number of colors required to color a vertex such that no two adjacent vertices have the same color. Okay, awesome. Well, and for example, actually, before we get back to chromatic number, let's talk about what we have done over here with this map. What we did was to convert a graph into a different graph, which we call its dual. So the dual of a graph is merely the graph that you get by putting a point in every region and connecting them. So for example, here's an example from the book, which I think is a good one. So suppose we have a particular graph which looks like this. Now, note that this a particular planar embedding is not necessarily the same as some other planar embedding of the graph, even though they are isomorphic. Okay, so these two graphs are isomorphic in the sense that they have the same number of vertices and the same number of edge relationships between them. Yet, this is a fundamentally different planar embedding than this graph. For example, how many regions does this graph have? Actually, they have the same number of regions. This is 1, 2, 3,